A metalloid is a chemical element that has properties in between those of metals and nonmetals. There is no standard definition of a metalloid, nor is there complete agreement as to which elements are appropriately classified as such. Despite this lack of specificity, the term remains in use in chemistry literature. The 6 commonly recognized metalloids are boron, silicon, germanium, arsenic, antimony and tellurium. Elements less commonly recognized as metalloids include carbon, aluminium, selenium, polonium and astatine. On a standard periodic table, all of these elements can be found in a diagonal region of the p block, extending from boron at one end to astatine at the other. Some periodic tables include a dividing line between metals and nonmetals, and it is generally the elements adjacent to this line or, less often, one or more of the elements adjacent to those elements, which are identified as metalloids. Typical metalloids have a metallic appearance, but they are brittle and only fair conductors of electricity. Chemically, they mostly behave as nonmetals. They can form alloys with metals. Most of their other physical and chemical properties are intermediate in nature. Metalloids are usually too brittle to have any structural uses. They and their compounds are used in alloys, biological agents, flame retardants, glasses, optical storage and optoelectronics, pyrotechnics, semiconductors and electronics. The electrical properties of silicon and germanium enabled the establishment of the semiconductor industry in the 1950s and the development of solid-state electronics from the early 1960s. The term metalloid originally referred to nonmetals. Its more recent meaning, as a category of elements with intermediate or hybrid properties, became widespread in 1940–1960. Metalloids are sometimes called semimetals, a practice that has been discouraged as the term semimetal has a different meaning in physics than in chemistry. In physics it more specifically refers to the electronic band structure of a substance. Broadly, the recognized metalloids occupy middle ground in terms of their abundance, extraction methods, and costs. Silicon is the second most abundant element in the Earth's crust after oxygen. Tellurium is rarer than gold, but more abundant than rhenium, the rarest of the stable metals. Extraction can be achieved by ordinary chemical reduction of the oxides or sulfides. Definitions: judgment-based, a metalloid is an element with properties that are in between, or a mixture of, the properties of metals and nonmetals, and thus is hard to classify as either a metal or a nonmetal. This is a generic definition that draws on metalloid attributes that are consistently cited in the literature. Difficulty of categorization is a key attribute. Most elements have a mixture of metallic and non-metallic properties, and can be classified according to which set of properties is more pronounced. Only the elements at or near the margins, lacking a sufficiently clear preponderance of either metallic or non-metallic properties, are classified as metalloids. Boron, silicon, germanium, arsenic, antimony and tellurium are commonly recognized as metalloids. Depending on the author, one or more from selenium, polonium or astatine are sometimes added to the list. Boron is sometimes excluded, by itself or with silicon. Tellurium is sometimes not regarded as a metalloid. The inclusion of antimony, polonium and astatine as metalloids has also been questioned. Other elements are occasionally classified as metalloids. These elements include hydrogen, beryllium, nitrogen, phosphorus, sulfur, zinc, gallium, tin, iodine, lead, bismuth and radon. The term metalloid has also been used for elements that exhibit metallic luster and electrical conductivity, and that are amphoteric, such as arsenic, antimony, vanadium, chromium, molybdenum, tungsten, tin, lead and aluminium. The other metals, and nonmetals that can form alloys with metals or modify their properties have also occasionally been considered as metalloids. Criteria-based, no widely accepted definition of a metalloid exists, nor any division of the periodic table into metals, metalloids and nonmetals. Hawkes questioned the feasibility of establishing a specific definition, noting that anomalies can be found in several attempted constructs. Classifying an element as a metalloid has been described by Sharp as arbitrary. The number and identities of metalloids depend on what classification criteria are used. Emslie recognized 4 metalloids. James et al. Listed 12. On average, 7 elements are included in such lists. Individual classification arrangements tend to share common ground and vary in the ill-defined margins. A single quantitative criterion such as electronegativity is commonly used, metalloids having electronegativity values from 1.8 or 1.9 to 2.2. Further examples include packing efficiency, the fraction of volume in a crystal structure occupied by atoms, and the Goldhammer-Hezeld criterion ratio. The commonly recognized metalloids have packing efficiencies of between 34% and 41%. The Goldhammer-Hezeld ratio, roughly equal to the cube of the atomic radius divided by the molar volume, is a simple measure of how metallic an element is, the recognized metalloids having ratios from around 0.85 to 1.1 and averaging 1.0. Other authors have relied on, for example, atomic conductance or bulk coordination number. Jones, writing on the role of classification in science, observed that classes are usually defined by more than 2 attributes. Masterton and Slowinski used 3 criteria to describe the 6 elements commonly recognized as metalloids. Metalloids have ionization energies around 200 kilocalories per mole and electronegativity values close to 2.0. They also said that metalloids are typically semiconductors, though antimony and arsenic have electrical conductivities approaching those of metals. Selenium and polonium are suspected as not in this scheme, while Astatine's status is uncertain. Periodic table territory, location. Metalloids lie on either side of the dividing line between metals and nonmetals. This can be found, in varying configurations, on some periodic tables. Elements to the lower left of the line generally display increasing metallic behavior. Elements to the upper right display increasing non-metallic behavior. When presented as a regular stair-step, elements with the highest critical temperature for their groups lie just below the line. The diagonal positioning of the metalloids represents an exception to the observation that elements with similar properties tend to occur in vertical groups. A related effect can be seen in other diagonal similarities between some elements and their lower right neighbors, specifically lithium-magnesium, beryllium-aluminium, and boron-silicon. Rainer Kahneman has argued that these similarities extend to carbon-phosphorus, nitrogen-sulfur, and into 3D block series. This exception arises due to competing horizontal and vertical trends in the nuclear charge. Going along a period, the nuclear charge increases with atomic number as there is an increase in electrons. The additional pull on outer electrons as nuclear charge increases generally outweighs the screening effect of having more electrons. With some irregularities, atoms therefore become smaller, ionization energy increases, and there is a gradual change in character, across a period, from strongly metallic, to weakly metallic, to weakly non-metallic, to strongly non-metallic elements. Going down a main group, the effect of increasing nuclear charge is generally outweighed by the effect of additional electrons being further away from the nucleus. Atoms generally become larger, ionization energy falls, and metallic character increases. The net effect is that the location of the metal-nonmetal transition zone shifts to the right in going down a group, and analogous diagonal similarities are seen elsewhere in the periodic table, as noted. Alternative treatments, depictions of metalloids vary according to the author. Some do not classify elements bordering the metal-nonmetal dividing line as metalloids, noting that a binary classification can facilitate the establishment of rules for determining bond types between metals and nonmetals. Metalloids are variously grouped with metals, regarded as nonmetals or treated as a subcategory of nonmetals. Other authors have suggested that classifying some elements as metalloids emphasizes that properties change gradually rather than abruptly as one moves across or down the periodic table. Some periodic tables distinguish elements that are metalloids and display no formal dividing line between metals and nonmetals. Metalloids are shown as occurring in a diagonal band or diffuse region. Properties: metalloids usually look like metals but behave largely like nonmetals. Physically, they are shiny, brittle solids with intermediate to relatively good electrical conductivity and the electronic band structure of a semimetal or semiconductor. Chemically, They mostly behave as nonmetals, have intermediate ionization energies and electronegativity values, and amphoteric or weakly acidic oxides. They can form alloys with metals. Most of their other physical and chemical properties are intermediate in nature. Compared to metals and nonmetals. Characteristic properties of metals, metalloids and nonmetals are summarized in the table. Physical properties are listed in order of ease of determination. Chemical properties run from general to specific, and then to descriptive. The above table reflects the hybrid nature of metalloids. The properties of form, appearance, and behavior when mixed with metals are more like metals. Elasticity and general chemical behavior are more like nonmetals. Electrical conductivity, band structure, ionization energy, electronegativity, and oxides are intermediate between the two. Common applications. The focus of this section is on the recognized metalloids. Elements less often recognized as metalloids are ordinarily classified as either metals or nonmetals. Some of these are included here for comparative purposes. Metalloids are too brittle to have any structural uses in their pure forms. They and their compounds are used as alloying components, biological agents, flame retardants, glasses, optical storage media and optoelectronics, pyrotechnics, semiconductors and electronics. Alloys. Writing early in the history of intermetallic compounds, the British metallurgist Cecil Deach observed that certain non-metallic elements are capable of forming compounds of distinctly metallic character with metals, and these elements may therefore enter into the composition of alloys. He associated silicon, arsenic and tellurium, in particular, with the alloy-forming elements. Phillips and Williams suggested that compounds of silicon, germanium, arsenic and antimony with B metals, are probably best classed as alloys. Among the lighter metalloids, alloys with transition metals are well represented. Boron can form intermetallic compounds and alloys with such metals of the composition Mnb, if N greater than 2. Ferroboron is used to introduce boron into steel. Nickel-boron alloys are ingredients in welding alloys and case-hardening compositions for the engineering industry. Alloys of silicon with iron and with aluminium are widely used by the steel and automotive industries, respectively. Germanium forms many alloys, most importantly with the coinage metals. The heavier metalloids continue the theme. Arsenic can form alloys with metals, including platinum and copper. It is also added to copper and its alloys to improve corrosion resistance and appears to confer the same benefit when added to magnesium. Antimony is well known as an alloy former, including with the coinage metals. Its alloys include pewter and type metal. Tellurium readily alloys with iron, as ferrotellurium, and with copper, in the form of copper tellurium. Ferrotellurium is used as a stabilizer for carbon and steel casting. Of the non-metallic elements less often recognized as metalloids, selenium Euro in the form of ferroselenium Euro is used to improve the machinability of stainless steels. Biological agents. All 6 of the elements commonly recognized as metalloids have toxic, dietary or medicinal properties. Arsenic and antimony compounds are especially toxic. Boron, silicon, and possibly arsenic, are essential trace elements. Boron, silicon, arsenic and antimony have medical applications, and germanium and tellurium are thought to have potential. Boron is used in insecticides and herbicides. It is an essential trace element. As boric acid, it has antiseptic, antifungal, and antiviral properties. Silicon is present in silatrane, a highly toxic rodenticide. Long-term inhalation of silica dust causes silicosis, a fatal disease of the lungs. Silicon is an essential trace element. Silicone gel can be applied to badly burned patients to reduce scarring. Salts of germanium are potentially harmful to humans and animals if ingested on a prolonged basis. There is interest in the pharmacological actions of germanium compounds but no licensed medicine as yet. Arsenic is notoriously poisonous and may also be an essential element in ultra-trace amounts. It has been used as a pharmaceutical agent since antiquity, including for the treatment of syphilis before the development of antibiotics. Arsenic is also a component of melarsopril, a medicinal drug used in the treatment of human African trypanosomiasis or sleeping sickness. In 2003, arsenic trioxide was reintroduced for the treatment of acute promyelocytic leukemia, a cancer of the blood and bone marrow. Metallic antimony is relatively non-toxic, but most antimony compounds are poisonous. Two antimony compounds, sodium stibogluconate and stibophene, are used as antiparasitical drugs. Elemental tellurium is not considered particularly toxic. 2 grams of sodium tellurate, if administered, can be lethal. People exposed to small amounts of airborne tellurium exude a foul and persistent garlic-like odor. Tellurium dioxide has been used to treat sporadic dermatitis. Other tellurium compounds were used as antimicrobial agents before the development of antibiotics. In future, such compounds may need to be substituted for antibiotics that have become ineffective due to bacterial resistance. Of the elements less often recognized as metalloids, beryllium and lead are noted for their toxicity. Lead arsenate has been extensively used as an insecticide. Sulfur is one of the oldest of the fungicides and pesticides. Phosphorus, sulfur, zinc, selenium and iodine are essential nutrients, and aluminium, tin and lead may be. Sulfur, gallium, selenium, iodine and bismuth have medicinal applications. Sulfur is a constituent of sulfonamide drugs, still widely used for conditions such as acne and urinary tract infections. Gallium nitrate is used to treat the side effects of cancer. Gallium citrate, a radiopharmaceutical, facilitates imaging of inflamed body areas. Selenium sulfide is used in medicinal shampoos and to treat skin infections such as tinea versicolor. Iodine is used as a disinfectant in various forms. Bismuth is an ingredient in some antibacterials. Flame retardants, compounds of boron, silicon, arsenic and antimony have been used as flame retardants. Boron, in the form of borax, has been used as a textile flame retardant since at least the 18th century. Silicon compounds such as silicons, silanes, silzeskioxane, silica and silicates, some of which were developed as alternatives to more toxic halogenated products, can considerably improve the flame retardancy of plastic materials. Arsenic compounds such as sodium arsenite or sodium arsenate are effective flame retardants for wood but have been less frequently used due to their toxicity. Antimony trioxide is a flame retardant. Aluminium hydroxide has been used as a wood fiber, rubber, plastic and textile flame retardant since the 1890s. Apart from aluminium hydroxide, use of phosphorus-based flame retardants in the form of, for example, organophosphate now exceeds that of any of the other main retardant types. These employ boron, antimony or halogenated hydrocarbon compounds. Glass formation. The oxides B2O3, CO2, GO2, As2O3 and Sb2O3 readily form glasses. TeO2 forms a glass but this requires a heroic quench rate, or the addition of an impurity, otherwise the crystalline form results. These compounds are used in chemical, domestic and industrial glassware and optics. Boron trioxide is used as a glass fiber additive, and is also a component of borosilicate glass, widely used for laboratory glassware and domestic ovenware for its low thermal expansion. Most ordinary glassware is made from silicon dioxide. Germanium dioxide is used as a glass fiber additive, as well as in infrared optical systems. Arsenic trioxide is used in the glass industry as a decolorizing and thinning agent, as is antimony trioxide. Tellurium dioxide finds application in laser and nonlinear optics. Amorphous metallic glasses are generally most easily prepared if one of the components is a metalloid or near metalloid such as boron, carbon, silicon, phosphorus or germanium. Aside from thin films deposited at very low temperatures, the first known metallic glass was an alloy of composition or 75C25 reported in 1960. A metallic glass having a strength and toughness not previously seen, of composition PD82.5 P6C9.5 GE2, was reported in 2011. Phosphorus, selenium and lead, which are less often recognized as metalloids, are also used in glasses. phosphate glass as a substrate of phosphorus pentoxide, rather than the silica of conventional silicate glasses. It is used, for example, to make sodium lamps. Selenium compounds can be used both as decolorizing agents and to add a red color to glass. Decorative glassware made of traditional lead glass contains at least 30% lead, oxide. Lead glass used for radiation shielding may have up to 65% PbO. Lead-based glasses have also been extensively used in electronics components, enameling, sealing and glazing materials, and solar cells. Bismuth-based oxide glasses have emerged as a less toxic replacement for lead in many of these applications. Optical storage and optoelectronics, varying compositions of GeSbTe and Ag and indoped Sb2Te, being examples of phase change materials, are widely used in rewritable optical discs and phase change memory devices. By applying heat, they can be switched between amorphous and crystalline states. The change in optical and electrical properties can be used for information storage purposes. Future applications for GeSbTe may include ultrafast, entirely solid-state displays with nanometer-scale pixels, semi-transparent Smart unregistered trademark glasses, Smart unregistered trademark contact lenses and artificial retina devices. Pyrotechnics. The recognized metalloids have either pyrotechnic applications or associated properties. Boron and silicon are commonly encountered. They act somewhat like metal fuels. Boron is used in pyrotechnic initiator compositions, and in delay compositions that burn at a constant rate. Boron carbide has been identified as a possible replacement for more toxic barium or hexachloroethane mixtures in smoke munitions, signal flares and fireworks. Silicon, like boron, is a component of initiator and delay mixtures. Doped germanium can act as a variable speed Thermite fuel. Arsenic trisulfide American Samoa, 2S3, was used in old naval signal lights, in fireworks to make white stars, in yellow smoke screen mixtures, and in initiator compositions. Antimony trisulfide Sb2S3 is found in white light fireworks and in flash and sound mixtures. Tellurium has been used in delay mixtures and in blasting cap initiator compositions. Carbon, aluminium, phosphorus and selenium continue the theme. Carbon, in black powder, is a constituent of fireworks rocket propellants, bursting charges, and effects mixtures, and military delay fuses and igniters. Aluminium is a common pyrotechnic ingredient, and is widely employed for its capacity to generate light and heat, including in thermite mixtures. Phosphorus can be found in smoke and incendiary munitions, paper caps used in toy guns, and party poppers. Selenium has been used in the same way as tellurium. Semiconductors and electronics. All the elements commonly recognized as metalloids have been used in the semiconductor or solid-state electronic industries. Some properties of boron have limited its use as a semiconductor. It has a high melting point, single crystals are relatively hard to obtain, and introducing and retaining controlled impurities is difficult. Silicon is the leading commercial semiconductor. It forms the basis of modern electronics and information and communication technologies. This was despite the study of semiconductors, early in the 20th century, having been regarded as the physics of dirt, and not deserving of close attention. Germanium has largely been replaced by silicon in semiconducting devices, being cheaper, more resilient at higher operating temperatures, and easier to work during the microelectronic fabrication process. Germanium is still a constituent of semiconducting silicon-germanium alloys, and these have been growing in use, particularly for wireless communication devices. Such alloys exploit the higher carrier mobility of germanium. The synthesis of gram-scale quantities of semiconducting germanium was reported in 2013. This comprises 1-atom-thick sheets of hydrogen-terminated germanium atoms, analogous to graphene. It conducts electrons more than 10 times faster than silicon and 5 times faster than germanium, and is thought to have potential for optoelectronic and sensing applications. The development of a germanium wire-based anode that more than doubles the capacity of lithium-ion batteries was reported in 2014. In the same year, Li et al. Reported that defect-free crystals of graphene large enough to have electronic uses could be grown on, and removed from, a germanium substrate. Arsenic and antimony are not semiconductors in their standard states. Both form type 3V semiconductors in which the average number of valence electrons per atom is the same as that of group 14 elements. These compounds are preferred for some special applications. Antimony nanocrystals may enable lithium-ion batteries to be replaced by more powerful sodium-ion batteries. Tellurium, which is a semiconductor in its standard state, is used mainly as a component in type 2,6 semiconducting chalcogenides. These have applications in electro-optics and electronics. Cadmium telluride is used in solar modules for its high conversion efficiency, low manufacturing costs, and large band gap of 1.44 eV, letting it absorb a wide range of wavelengths. Bismuth telluride, alloyed with selenium and antimony, is a component of thermoelectric devices used for refrigeration or portable power generation. 5 metalloids are boron, silicon, germanium, arsenic and antimony can be found in cell phones. Tellurium is expected to find such use. Of the less often recognized metalloids, phosphorus, gallium and selenium have semiconductor applications. Phosphorus is used in trace amounts as a dopant for N-type semiconductors. The commercial use of gallium compounds is dominated by semiconductor applications and integrated circuits. Cell phones. Laser diodes. Light-emitting diodes. Photodetectors. And solar cells. Selenium is used in the production of solar cells and in high-energy surge protectors. Nomenclature and history, derivation and other names. The word metalloid comes from the Latin metallum and the Greek oids. Several names are sometimes used synonymously, although some of these have other meanings that are not necessarily interchangeable: amphoteric element, boundary element, half metal, halfway element, near metal, meter metal, semiconductor, semimetal and submetal. Amphoteric element is sometimes used more broadly to include transition metals capable of forming oxyanions, such as chromium and manganese. Half metal is used in physics to refer to a compound or alloy that can act as a conductor and an insulator. Meter metal is sometimes used instead to refer to certain metals located just to the left of the metalloids on standard periodic tables. These metals are mostly diamagnetic and tend to have distorted crystalline structures, electrical conductivity values at the lower end of those of metals, and amphoteric oxides. Semimetal sometimes refers, loosely or explicitly, to metals with incomplete metallic character in crystalline structure, electrical conductivity or electronic structure. Examples include gallium, ytterbium, bismuth and neptunium. The names amphoteric element and semiconductor are problematic as some elements referred to as metalloids do not show marked amphoteric behavior or semiconductivity in their most stable forms. Origin and usage. The origin and usage of the term metalloid is convoluted. Its origin lies in attempts, dating from antiquity, to describe metals and to distinguish between typical and less typical forms. It was first applied in the early 19th century to metals that floated on water, and then more popularly to known metals. Earlier usage in mineralogy, to describe a mineral having a metallic appearance, can be sourced to as early as 1800. Since the mid-20th century it has been used to refer to intermediate or borderline chemical elements. The International Union of Pure and Applied Chemistry previously recommended abandoning the term metalloid, and suggested using the term semimetal instead. Use of this latter term has more recently been discouraged by Atkins et al. As it has a different meaning in physics, one that more specifically refers to the electronic band structure of a substance rather than the overall classification of an element. The most recent IUPAC publications on nomenclature and terminology do not include any recommendations on the usage of the terms metalloid or semimetal. Elements commonly recognized as metalloids. Properties noted in this section refer to the elements in their most thermodynamically stable forms under ambient conditions. Boron. Pure boron is a shiny, silver-gray crystalline solid. It is less dense than aluminium, and is hard and brittle. It is barely reactive under normal conditions, except for attack by fluorine, and has a melting point of 2076 degrees Celsius. Boron is a semiconductor. Its room temperature electrical conductivity is 1.5 A, 10^6 Euro-cent-gmar-1 and a band gap of about 1.56 eV. The chemistry of boron is dominated by its small atomic size, and relatively high ionization energy. With only 3 valence electrons, simple covalent bonding cannot fulfill the octet rule. Metallic bonding is the usual result among the heavier congeners of boron, but this generally requires a low ionization energy. Being small and having a high ionization energy, boron instead forms delocalized covalent bonds, in which 3 atoms share 2 electrons. The associated structural unit, the icosahedral B12 cluster, pervades the allotropic forms of boron. The same motif can be seen, as a deltahedral variants or fragments, in metal borides and hydride derivatives, and in some halides. The bonding in boron has been described as being characteristic of behavior intermediate between metals and non-metallic covalent network solids. The energy required to transform B, C, N, C and P from non-metallic to metallic states has been estimated as 3100, 240, 33 and 50 kilojoules per mole, respectively. This indicates how close boron is to the metal-nonmetal borderline. Most of the chemistry of boron is non-metallic in nature. The small size of the boron atom enables the preparation of many interstitial alloy-type borides. Analogies between boron and transition metals have been noted in the formation of complexes, and deducts 4+CO Company, 5, as well as in the geometric and electronic structures of cluster species such as B6H6, 2 Euro, and Ru6, CO, 18, 2 Euro. The aqueous chemistry of boron is characterized by the formation of many different polar borate anions. Given its high charge-to-size ratio, nearly all compounds of boron are covalent, with a few complexed anionic and cationic species. Boron has a strong affinity for oxygen and a duly extensive borate chemistry. The oxide B2O3 is polymeric in structure, weakly acidic, and a glass former. Organometallic compounds of boron have been known since the 19th century. Silicon. Silicon is a crystalline solid with a blue-gray metallic luster. Like boron, it is less dense than aluminium, and is hard and brittle. It is a relatively unreactive element. According to Rocco, the massive crystalline form is remarkably inert to all acids, including hydrofluoric. Less pure silicon, and the powdered form, are variously susceptible to attack by strong or heated acids, as well as by steam and fluorine. Silicon dissolves in hot aqueous alkalis with the evolution of hydrogen, as do metals such as beryllium, aluminium, zinc, gallium or indium. It melts at 1414 degrees Celsius. Silicon is a semiconductor with an electrical conductivity of 10^4 Euro-cent-gmar-1 and a band gap of about 1.11 eV. When it melts, silicon becomes a reasonable metal with an electrical conductivity of 1.0 Euro 1.3 104 Euro-cent-gmar-1, similar to that of liquid mercury. The chemistry of silicon is generally non-metallic in nature. It can form alloys with metals such as iron and copper. Silicon shows fewer tendencies to anionic behavior than ordinary nonmetals. Its solution chemistry is characterized by the formation of oxyanions. The high strength of the silicon-oxygen bond dominates the chemical behavior of silicon. Polymeric silicates, built up by tetrahedral CO4 units sharing their oxygen atoms, are the most abundant and important compounds of silicon. The polymeric borates, comprising linked trigonal and tetrahedral BO3 or BO4 units, are built on similar structural principles. The oxide CO2 is polymeric in structure, weakly acidic, and a glass former. Traditional organometallic chemistry includes the carbon compounds of silicon. Germanium. Germanium is a shiny gray-white solid. It has a density of 5.323 grams per centimeter 3 and is hard and brittle. It is mostly unreactive at room temperature but is slowly attacked by hot concentrated sulfuric or nitric acid. Germanium also reacts with molten caustic soda to yield sodium germanate Na2GO3 and hydrogen gas. It melts at 938 degrees Celsius. Germanium is a semiconductor with an electrical conductivity of around 2×10⁻² eurocentgmar1 and a band gap of 0.67 eV. Liquid germanium is a metallic conductor, with an electrical conductivity similar to that of liquid mercury. Most of the chemistry of germanium is characteristic of a known metal. It can form alloys with metals such as aluminium and gold. Germanium shows fewer tendencies to anionic behavior than ordinary known metals. Its solution chemistry is characterized by the formation of oxyanions. Germanium generally forms tetravalent compounds, and it can also form less stable divalent compounds, in which it behaves more like a metal. Germanium analogues of all of the major types of silicates have been prepared. The metallic character of germanium is also suggested by the formation of various oxyacid salts. A phosphate, HPO4, 2KH2O, and highly stable trifluoroacetate GE, OCOCF3, 4 have been described, as have GE2, SO4, 2, GE, ClO4, 4 and GEH2, C2O4, 3. The oxide GO2 is polymeric, amphoteric, and a glass former. The dioxide is soluble in acidic solutions, and this is sometimes used to classify germanium as a metal. Up to the 1930s, germanium was considered to be a poorly conducting metal. It has occasionally been classified as a metal by later writers. As with all the elements commonly recognized as metalloids, germanium has an established organometallic chemistry. Arsenic. Arsenic is a gray, metallic-looking solid. It has a density of 5.727 grams per centimeter 3 and is brittle, and moderately hard. It is stable in dry air but develops a golden-bronze patina in moist air, which blackens on further exposure. Arsenic is attacked by nitric acid and concentrated sulfuric acid. It reacts with fused caustic soda to give the arsenate Na3SO3 and hydrogen gas. Arsenic sublimes at 615 degrees Celsius. The vapor is lemon yellow and smells like garlic. Arsenic only melts under a pressure of 38.6 atmospheres, at 817 degrees Celsius. It is a semimetal with an electrical conductivity of around 3.9 104 eurocentgmar1 and a band overlap of 0.5 eV. Liquid arsenic is a semiconductor with a band gap of 0.15 eV. The chemistry of arsenic is predominantly non-metallic. Its many metal alloys are mostly brittle. Arsenic shows fewer tendencies to anionic behavior than ordinary known metals. Its solution chemistry is characterized by the formation of oxyanions. Arsenic generally forms compounds in which it has an oxidation state of +3 or +5. The halides, and the oxides and their derivatives are illustrative examples. In the trivalent state, arsenic shows some incipient metallic properties. The halides are hydrolyzed by water but these reactions, particularly those of the chloride, are reversible with the addition of a hydrohalic acid. The oxide is acidic but, as noted below, amphoteric. The higher, less stable, pentavalent state has strongly acidic properties. Compared to phosphorus, the stronger metallic character of arsenic is indicated by the formation of oxyacid salts such as AsPO4, As2, SO4, 3 and arsenic acetate as, CH3COO, 3. The oxide As2O3 is polymeric, amphoteric, and a glass former. Arsenic has an extensive organometallic chemistry. Antimony. Antimony is a silver-white solid with a blue tint and a brilliant luster. It has a density of 6.697 grams per centimeter 3 and is brittle, and moderately hard. It is stable in air and moisture at room temperature. It is attacked by concentrated nitric acid, yielding the hydrated pentoxide Sp2O5. Aqua regia gives the pentachloride SbCl5 and hot concentrated sulfuric acid results in the sulfate Sp2, SO4, 3. It is not affected by molten alkali. Antimony is capable of displacing hydrogen from water, when heated, 2Sb plus 3 hours 20 Sb2O3 plus 3 hours 2. It melts at 631 degrees Celsius. Antimony is a semimetal whose electrical conductivity is around 3.1 A, 104 Euro-cent-gmar1 and a band overlap of 0.16 eV. Liquid antimony is a metallic conductor with an electrical conductivity of around 5.3 A, 104 Euro-cent-gmar1. Most of the chemistry of antimony is characteristic of a known metal. It can form alloys with one or more metals such as aluminium, iron, nickel, copper, zinc, tin, lead and bismuth. Antimony has fewer tendencies to anionic behavior than ordinary known metals. Its solution chemistry is characterized by the formation of oxyanions. Like arsenic, antimony generally forms compounds in which it has an oxidation state of +3 or +5. The halides, and the oxides and their derivatives are illustrative examples. The +5 state is less stable than the +3, but relatively easier to attain than with arsenic. This is explained by the poor shielding afforded the arsenic nucleus by its 3d10 electrons. In comparison, the tendency of antimony to oxidize more easily partially offsets the effect of its 4d10 shell. Tripositive antimony is amphoteric. Pentapositive antimony is acidic. Consistent with an increase in metallic character down group 15, antimony forms salts or salt-like compounds including nitrate Sb, NO3, 3, phosphate Sb-PO4, sulfate Sb2, SO4, 3 and perchlorate Sb, ClO4, 3. The otherwise acidic pentoxide Sb2O5 shows some basic behavior in that it can be dissolved in very acidic solutions, with the formation of the oxidation SbO+, 2. The oxide Sb2O3 is polymeric, amphoteric, and a glass former. Antimony has an extensive organometallic chemistry. Tellurium. Tellurium is a silvery white shiny solid. It has a density of 6.24 grams per centimeter 3, is brittle, and is the softest of the commonly recognized metalloids, being marginally harder than sulfur. Large pieces of tellurium are stable in air. The finely powdered form is oxidized by air in the presence of moisture. Tellurium reacts with boiling water, or when freshly precipitated even at 50 AA degrees Celsius, to give the dioxide and hydrogen, Te plus 2 hours 2 or TeO2 plus 2 hours 2. It reacts with nitric, sulfuric and hydrochloric acids to give compounds such as the sulfoxide TeSO3 or tellurous acid H2TeO3, the basic nitrate plus, NO3, a euro, or the oxide sulfate Te2O3, SO4. It dissolves in boiling alkalis, to give the tellurite and telluride, 3Te plus 6KOH equals K2TeO3 plus 2K2Te plus 3 hours 2O, a reaction that proceeds or is reversible with increasing or decreasing temperature. At higher temperatures tellurium is sufficiently plastic to extrude. It melts at 449.51 degrees Celsius. Crystalline tellurium has a structure consisting of parallel infinite spiral chains. The bonding between adjacent atoms in a chain is covalent, but there is evidence of a weak metallic interaction between the neighboring atoms of different chains. Tellurium is a semiconductor with an electrical conductivity of around 1.0 Euro-cent-gmar1 and a band gap of 0.32 to 0.38 eV. Liquid tellurium is a semiconductor, with an electrical conductivity, on melting, of around 1.9 A, 103 Euro-cent-gmar1. Superheated liquid tellurium is a metallic conductor. Most of the chemistry of tellurium is characteristic of a known metal. It can form alloys with aluminium, silver and tin. Tellurium shows fewer tendencies to anionic behavior than ordinary known metals. Its solution chemistry is characterized by the formation of oxyanions. Tellurium generally forms compounds in which it has an oxidation state of a 2, +4 or +6. The +4 state is the most stable. Tellurides of composition XXTEY are easily formed with most other elements and represent the most common tellurium minerals. Non-stoichiometry is pervasive, especially with transition metals. Many tellurides can be regarded as metallic alloys. The increase in metallic character evident in tellurium, as compared to the lighter chalcogens, is further reflected in the reported formation of various other oxyacid salts, such as a basic selenate 2-TeO2-SaO3 and an analogous perchlorate and periodate 2-TeO2-HXO4. Tellurium forms a polymeric, amphoteric, glass-forming oxide TeO2. The latter is a conditional glass-forming oxide. It forms a glass with a very small amount of additive. Tellurium has an extensive organometallic chemistry. Elements less commonly recognized as metalloids. Carbon. Carbon is ordinarily classified as a known metal but has some metallic properties and is occasionally classified as a metalloid. Hexagonal graphitic carbon is the most thermodynamically stable allotrope of carbon under ambient conditions. It has a lustrous appearance and is a fairly good electrical conductor. Graphite has a layered structure. Each layer comprises carbon atoms bonded to 3 other carbon atoms in a honeycomb lattice arrangement. The layers are stacked together and held loosely by van der Waals forces and delocalized valence electrons. Like a metal, the conductivity of graphite in the direction of its planes decreases as the temperature is raised. It has the electronic band structure of a semimetal. The allotropes of carbon, including graphite, can accept foreign atoms or compounds into their structures via substitution, intercalation or doping. The resulting materials are referred to as carbon alloys. Carbon can form ionic salts, including a hydrogen sulfate, perchlorate, and nitrate, C+, 24 0.2Hx, where X equals HSO4. ClO4, and C+, 24 No Euro, 3.3 HNO3. In organic chemistry, carbon can form complex cations termed carbocations in which the positive charge is on the carbon atom. Examples are CH+, 3 and CH+, 5, and their derivatives. Carbon is brittle, and behaves as a semiconductor in a direction perpendicular to its planes. Most of its chemistry is non-metallic. It has a relatively high ionization energy and, compared to most metals, a relatively high electronegativity. Carbon can form anions such as C4 C2 2 and C3 4, in compounds with metals of main groups 1 3, and with the lanthanides and actinides. Its oxide CO2 forms carbonic acid H2CO3. Aluminium. Aluminium is ordinarily classified as a metal. It is lustrous, malleable and ductile, and has high electrical and thermal conductivity. Like most metals, it has a close-packed crystalline structure, and forms a cation in aqueous solution. It has some properties that are unusual for a metal. Taken together, these are sometimes used as a basis to classify aluminium as a metalloid. Its crystalline structure shows some evidence of directional bonding. Aluminium bonds covalently in most compounds. The oxide Al2O3 is amphoteric, and a conditional glass former. Aluminium can form anionic aluminates, such behavior being considered non-metallic in character. Classifying aluminium as a metalloid has been disputed given its many metallic properties. It is therefore, arguably, an exception to the mnemonic that elements adjacent to the metal-known metal dividing line are metalloids. Stott labels aluminium as a weak metal. It has the physical properties of a metal but some of the chemical properties of a known metal. Steele notes the paradoxical chemical behavior of aluminium. It resembles a weak metal in its amphoteric oxide and in the covalent character of many of its compounds. Yet it is a highly electropositive metallar, with a high negative electrode potential. Selenium. Selenium shows borderline metalloid or known metal behavior. Its most stable form, the gray trigonal allotrope, is sometimes called metallic selenium because its electrical conductivity is several orders of magnitude greater than that of the red monoclinic form. The metallic character of selenium is further shown by its luster and its crystalline structure, the latter of which is thought to include weakly metallic interchain bonding. Selenium can be drawn into thin threads when molten and viscous. It shows reluctance to acquire the high positive oxidation numbers characteristic of known metals. It can form cyclic polycations, such as say 2+, 8, when dissolved in alliums, and a hydrolyzed cationic salt in the form of trihydroxyselenium perchlorate, say, OH, 3, plus a ClOa 4. The non-metallic character of selenium is shown by its brittleness and the low electrical conductivity of its highly purified form. This is comparable to or less than that of bromine, a known metal. Selenium has the electronic band structure of a semiconductor and retains its semiconducting properties in liquid form. It has a relatively high electronegativity. Its reaction chemistry is mainly that of its non-metallic anionic forms Se2A, SaO2A, 3 and SaO2A, 4. Selenium is commonly described as a metalloid in the environmental chemistry literature. It moves through the aquatic environment similarly to arsenic and antimony. Its water-soluble salts, in higher concentrations, have a similar toxicological profile to that of arsenic. Polonium. Polonium is distinctly metallic in some ways. Both of its allotropic forms are metallic conductors. It is soluble in acids, forming the rose-colored Po2 plus cation and displacing hydrogen, Po plus 2 hours plus a Po2 plus H2. Many polonium salts are known. The oxide Po2 is predominantly basic in nature. Polonium is a reluctant oxidizing agent. Unlike its lighter congener oxygen, highly reducing conditions are required for the formation of the Po2A anion in aqueous solution. Whether polonium is ductile or brittle is unclear. It is predicted to be ductile based on its calculated elastic constants. It has a simple cubic crystalline structure. Such a structure has few slip systems and leads to very low ductility and hence low fracture resistance. Polonium shows non-metallic character in its halides, and by the existence of polonides. The halides have properties generally characteristic of known metal halides. Many metal polonides, obtained by heating the elements together at 500 1000 AA degrees Celsius, and containing the Po2A anion, are also known. Astatine. As a halogen, astatine tends to be classified as a known metal. It has some marked metallic properties and is sometimes instead classified as either a metalloid or as a metal. Immediately following its production in 1940, early investigators considered it a metal. In 1949 it was called the most noble known metal as well as being a relatively noble metal. In 1950 astatine was described as a halogen and a reactive known metal. In 2013, on the basis of relativistic modeling, astatine was predicted to be a monatomic metal, with a face-centered cubic crystalline structure. Several authors have commented on the metallic nature of some of the properties of astatine. Since iodine is a semiconductor in the direction of its planes, and since the halogens become more metallic with increasing atomic number, it has been presumed that astatine would be a metal if it could form a condensed phase. Astatine may be metallic in the liquid state on the basis that elements with an enthalpy of vaporization greater than 42 kJ per mole are metallic when liquid. Such elements include boron, silicon, germanium, antimony, selenium and tellurium. Estimated values for HVAP of diatomic astatine are 50 kJ per mole or higher. Diatomic iodine, with AlHVAP of 41.71, falls just short of the threshold figure. Like typical metals, astatine is precipitated by hydrogen sulfide even from strongly acid solutions and is displaced in a free form from sulfate solutions. It is deposited on the cathode on electrolysis. Further indications of a tendency for astatine to behave like a metal are the formation of pseudo-ylide compounds, complexes of astatine cations, complex anions of trivalent astatine A, as well as complexes with a variety of organic solvents. It has also been argued that astatine demonstrates cationic behavior, by way of stable at plus and at O plus forms, in strongly acidic aqueous solutions. Some of astatine's reported properties are non-metallic. It is the narrow liquid range ordinarily associated with known metals. Batson gives a calculated band gap energy for astatine of 0.70 eV. This is consistent with known metals having separated valence and conduction bands and thereby being either semiconductors or insulators. The chemistry of astatine in aqueous solution is mainly characterized by the formation of various anionic species. Most of its known compounds resemble those of iodine, which is a halogen and a known metal. Such compounds include astatides, astatates, and monovalent interhalogen compounds. Restrepo al. reported that astatine appeared to be more polonium-like than halogen-like. They did so on the basis of detailed comparative studies of the known and interpolated properties of 72 elements. Related concepts, near metalloids. In the periodic table, some of the elements adjacent to the commonly recognized metalloids, although usually classified as either metals or known metals, are occasionally referred to as near metalloids or noted for their metalloidal character. To the left of the metal-known metal dividing line, such elements include gallium, tin and bismuth. They show unusual packing structures, marked covalent chemistry, and amphoterism. To the right of the dividing line are carbon, phosphorus, selenium and iodine. They exhibit metallic luster, semiconducting properties and bonding or valence bands with delocalized character. This applies to their most thermodynamically stable forms under ambient conditions, carbon as graphite, phosphorus as black phosphorus, and selenium as gray selenium. Allotropes. Different crystalline forms of an element are called allotropes. Some allotropes, particularly those of elements located alongside or near the notional dividing line between metals and known metals, exhibit more pronounced metallic, metalloidal or non-metallic behavior than others. The existence of such allotropes can complicate the classification of the elements involved. Tin, for example, has two allotropes, tetragonal white I squared tin and cubic gray I plus or minus tin. White tin is a very shiny, ductile and malleable metal. It is the stable form at or above room temperature and has an electrical conductivity of 9.17 A, 104 Izark-Ma1. Gray tin usually has the appearance of a gray microcrystalline powder, and can also be prepared in brittle semi-lustrous crystalline or polycrystalline forms. It is the stable form below 13.2 AA degree Celsius and has an electrical conductivity of between A, 102 Izark-Ma1. Gray tin has the same crystalline structure as that of diamond. It behaves as a semiconductor, but has the electronic band structure of a semimetal. It has been referred to as either a very poor metal, a metalloid, a known metal or a near metalloid. The diamond allotrope of carbon is clearly non-metallic, being translucent and having a low electrical conductivity of 10^14 to 10^16 Izark-Ma1. Graphite has an electrical conductivity of 3A, 104 Izark-Ma1, a figure more characteristic of a metal. Phosphorus, sulfur, arsenic, selenium, antimony and bismuth also have less stable allotropes that display different behaviors. Abundance, extraction and cost. Abundance. The table gives crustal abundances of the elements commonly to rarely recognized as metalloids. Some other elements are included for comparison: oxygen and xenon. Iron and the coinage metals copper, silver and gold. And rhenium, the least abundant stable metal. Various abundance estimates have been published. These often disagree to some extent. Extraction. The recognized metalloids can be obtained by chemical reduction of either their oxides or their sulfides. Simpler or more complex extraction methods may be employed depending on the starting form and economic factors. Boron is routinely obtained by reducing the trioxide with magnesium, B2O3 plus 3 mg or 2B plus 3 MgO. After secondary processing, the resulting brown powder has a purity of up to 97%. Boron of higher purity is prepared by heating volatile boron compounds, such as BCl3 or BBr3, either in a hydrogen atmosphere or to the point of thermal decomposition. Silicon and germanium are obtained from their oxides by heating the oxide with carbon or hydrogen, CO2 plus CaC plus CO2. GO2 plus 2 hours duo GE plus 2 hours duo. Arsenic is isolated from its pyrite or arsenical pyrite by heating. Alternatively, It can be obtained from its oxide by reduction with carbon, 2s2O3 plus 3Ca2s plus 3CO2. Antimony is derived from its sulfide by reduction with iron, Sb2s3O2Sb plus 3Fe. Tellurium is prepared from its oxide by dissolving it in aqueous NaO, yielding tellurite, then by electrolytic reduction, TeO2 plus 2NaO and Na2TeO3 plus H2O. Na2TeO3 plus H2O or Te plus 2NaO plus O2. Another option is reduction of the oxide by roasting with carbon, TeO2 plus C or Te plus CO2. Production methods for the elements less frequently recognized as metalloids involve natural processing, electrolytic or chemical reduction, or irradiation. Carbon occurs naturally and is extracted by crashing the parent rock and floating a lighter graphite to the surface. Aluminium is extracted by dissolving its oxide Al2O3 in molten cryolite Na3Al6 and then by high-temperature electrolytic reduction. Selenium is produced by roasting its coinage metal selenides X2Se with soda ash to give the selenite, X2Se plus O2 plus Na2CO3 and Na2CO3 plus 2X plus CO2. The selenide is neutralized by sulfuric acid H2SO4 to give selenous acid H2CO3. This is reduced by bubbling with SO2 to yield elemental selenium. Polonium and astatine are produced in minute quantities by irradiating bismuth. Cost: the recognized metalloids and their closer neighbors mostly cost less than silver. Only polonium and astatine are more expensive than gold. As of April 5, 2014, prices for small samples of silicon, antimony and tellurium, and graphite, aluminium and selenium, average around one-third the cost of silver. Boron, germanium and arsenic samples average about 3.5 times the cost of silver. Polonium is available for about $100 per microgram, which is $100 million a gram. Zlutsky and Prosinski estimate a similar cost for producing astatine. Prices for the applicable elements traded as commodities tend to range from 2 to 3 times cheaper than the sample price, to nearly 3,000 times cheaper. Notes. Sources, citations. Indexed references. Further reading, Brady J.E., Humiston G. and Heikkinen H. 1980, Chemistry of the Representative Elements, Part 2, The Metalloids and Nonmetals, in General Chemistry, Principles and Structure, 2nd ed., SI version, John Wiley & Sons, New York, PPA 537 Euro 591, ISBN 0-471-06315-0, Cheat G. 1969, Halfway Elements, The Technology of Metalloids, Doubleday, New York, Chopin G. and Johnson RH 1972, Group 4 on the Metalloids, in Introductory Chemistry, Addison Wesley, Reading, Massachusetts. Pages 341 Euro 357, Dunstan S. 1968, The Metalloids, in Principles of Chemistry, D. Van Nostrand Company, London, PPA 407 Euro 39, Goldsmith RH 1982, Metalloids, Journal of Chemical Education, Volume 59, No. 6, PPA 526 Euro 527, doi, 10.1021/EDO59 P526, Hawks S.J. 2001, Semimetallicity, Journal of Chemical Education, Volume 78, No. 12, PPA 1686A. Euro 7, doi, 10.1021/EDO78 P1686, Metcalf H.C., Williams J. and Kastka J.F. 1974, Aluminum and the Metalloids, in Modern Chemistry, Holt, Reinhardt and Winston, New York, PPA 538 Euro 57, ISBN 0-03-089450-6, Moeller T., Baylor J.C., Klinberg J., Gus Company, Castellian M.E. and Metzi 1989, Carbon and the Semiconducting Elements, in Chemistry, with Inorganic Qualitative Analysis, 3rd ed., Harcourt Brace Jovanovic, San Diego, pp. A 751 Euro 75, ISBN 0-15-506492-4. Ricechem 1998, Metalloids, in Encyclopedia of Earth and Physical Sciences, Marshall Cavendish, New York, Volume 6, ppA 758-9, ISBN 0-7614-0551-8, Rocco E.G. 1966, The Metalloids, D.C. Heath and Company, Boston, Vernon R. E. 2013, Which Elements Are Metalloids? Journal of Chemical Education, Volume 90, No. 12, ppA 1703-7, doi, 10.1021/ed 3008457.